In this problem, we're asked to balance the following equation. And the reason why we do this is to make sure that the equation follows the law of conservation of mass, so anything on the reactant side also has to be on the product side. So we can start by looking at our copper here. And if we look on this side, we can see that we have one copper, and over here on this side, we also have one copper. So at the moment, that's fine. If we look here at the silver, we can see in this silver nitrate ion, we have one silver on this side, and we also have one silver here. But then the last thing we have to look at is the nitrate itself. So we have one nitrate on this side, but two on this side. So that means we need at least two nitrate ions to make this reaction balance, so this is a 2. And as such, now we have two silver on this side, making this silver also a 2. And just checking copper again, we can see we still have one here and one here. In part B of question 1, it asks us to balance the following combustion reaction. And how I find it easiest to balance combustion reactions is to assume and just start out as if you have only one of whatever hydrocarbon you have. So I'll just place this underneath as a placeholder. So assuming we have one of these, then that means we have 12 carbon atoms. And if we look over on this side, the only place carbon appears is in CO2. So that would mean we would need to have 12 of these. But you can't ignore the oxygen in the CO2 atoms. So having 12 oxygen here means we would also need to have 12 O2 atoms to go with the carbon atoms. Then, at this point, it's easy because H2O has a ratio of 2 to 1 hydrogen to oxygen, and we can see that same case is true for our hydrocarbon. So these 22 hydrogens pair up with these 11 oxygens to create 11 H2O, and then we can see that this was correct, so we can erase that and fill in. So question 2 asks us to write a skeleton equation for the following reactions. In the question A, we're asked to write the equation for the decomposition of calcium chloride into calcium and chlorine gas. So when writing a skeleton equation, it's always easiest to look at the reactants first. So calcium, having a positive 2 charge, is bound to the chloride with a positive 1 or negative 1 charge, making the chemical equation for that CaCl2, because the positive 2 here binds with the negative 2 here. Then this, because it's a decomposition reaction, goes into calcium and chlorine gas. Calcium, of course, just being Ca, and chlorine gas, because it is a diatomic ion, it requires 2 atoms, making it Cl2. And under a normal equation, we would need to balance this, but because you can see it's just a direct decomposition, there's no need to, because the 1 calcium over here translates to the 1 calcium over here, and the 2 chlorine over here translates to the Question 2 asks us to write the skeleton equation for B here, which is iron 3 reacting with oxygen gas to form iron oxide, so rust formation. So we know we have iron and oxygen gas, which we already know chemical equation for. That's Fe plus O2 goes into, here's where we have to do a little bit of thinking. Iron has a charge of 3, and oxide has one oxygen molecule has a charge of negative 2. So through swap and drop, we know you have Fe2O3. Now all that's left to do is balance this. So it's a little bit tricky to balance, but if we look, we have 3 oxygen here and 2 here, so we need to increase the amount here to 2. This becomes a 3, and since we have 4 irons on this side, we need 4 here. Question 3 asks us to predict the products of the double replacement reaction in both words and the skeleton equation. So because we know it's double replacement, you can just take the first term of the first and the second term of the second and combine them, creating silver chromate.
you can take the second term of the first and the first term of the second to get potassium nitrate. So now we must write out the balanced chemical equation for this. So the equation for silver nitrate is AgNO3 plus potassium chromate, which is K2CrO4. And that goes into silver chromates, which is Ag2CrO4, and potassium nitrate, which is KNO3. And now all that's left to do is balance. So we can see we have 1 silver over here, but 2 over here, so this must be a 2. Over here we have 1 potassium, but we have 2 over here, so this must be a 1, and this must be a 2. And then, consequently, that makes this a 1. Question 4 asks us to identify the following reaction types. So the easiest way to identify a reaction type is look at the product, the number of products and the number of reactants. So here we can see we have 2 products equaling 2 reactants equaling 1 product, meaning this is a synthesis reaction because these 2 reactants are being synthesized into 1 product. So that's a synthesis. So, and then this one, you may be inclined to think it's a double replacement because there's 2 reactants and 2 products, but if you look, we have a hydrocarbon and an oxygen, which is a telltale sign that it is a combustion reaction.
Okay, the question asks us, what mass of ammonium chlorate should be used for 1 kilogram of aluminum? So, they give us 1 kilogram of aluminum. We just want to convert it to mass of ammonium chlorate. So, we'll start off with our train tracks, 1 kilogram of aluminum, right? And then our periodic table gives us grams. So it would be nice if we converted kilograms to grams. For every 1 kilogram of aluminum, there's 1,000 grams. And then we can use our periodic table to convert grams to moles. So if we look at aluminum, there are 26.98 grams per mole. So we have 1 mole. And we convert that to 26.98 grams. And then we'll convert those moles from 3 moles to 3 moles. That's a 1-to-1. So for every 3 moles of the ammonium, I'm not going to write it out, we get 3 moles of aluminum. And then we want moles to grams or kilograms. So we'll convert that. We have moles. We can look at our periodic table. So we have 1 nitrogen. We look for nitrogen. It's 14.01, and then we have 4 hydrogen. So we have 4 times 1.008. Then we also have a chlorine and 4 oxygen. So we'll add the chlorine. Chlorine's molar mass is 35.45, and then 4 times oxygen. Oxygen has a molar mass of 16. And that's for every 1 mole of the ammonium chloride. And then if you do that math, the 1 times the 1,000 times the 3 times 14, all this addition. And we divide, we get 117. And notice there's only one sig fig, so we'll round to 100, and that's in grams. Oh, divided by 26.9. And what is that? We're gonna have Nick do that. And it's 4.37, but again, sig fig, so 4 grams.
Okay, in this problem, we are asked to first balance this complicated equation and then find the number of moles of NH4SCN that are needed to react with 6.5 grams of barium hydroxide octahydrate. So first, to balance, we start, and just to get this over with, we have 3 moles of this, 6 moles of this, 3 this, 30, and 6. Okay, and to start, we're going to use our stoichiometry to start with 6.5 grams. BA OH H2O. Okay, and then 1 mole of that is 315.474. Okay, and in this equation there are 3 moles of that. And for every 3 moles of that, we have 6 moles of NH4SCN. Okay? So that'll get us to 1 moles. Pretty nice, easy to use. And we put that in our calculator. And we get 6. L equals 0.04 grams of NH4SCN. Cut. Oh my god.
Okay, so the question asked if there's 26 grams of this and 50 grams of that. Those are both these 2 reactants here. How many of grams will form? So first we need to find the limiting reactant, because once the limiting reactant runs out, the reaction will stop. So we need to convert these grams here to moles. So we'll do 26 grams of the ammonium compound there. And we'll convert, so we need to find the molar mass. Now, we look at nitrogen here. There's 1 nitrogen, so there's actually 2 nitrogens. So 14, say, times 2 is 28. And then there's 4 hydrogens, that's 4, because the molar mass of hydrogen is 1. There's 1 sulfur. Sulfur has a molar mass of 32. And there's 1 carbon. Carbon has a molar mass of 12. And that's grams. And then we have per mole. The grams and grams cancel out. Then we're left with, just plug it into your calculator, 28 plus 4 plus 32 plus 12 gives you 76 grams. And then you do 26 divided by 76. so 0.34 moles. Next, we will go over here and we'll convert these 50 grams of the barium hydrate thing. I won't write it all out. And the mole mass of barium is around 137. Plus, we have 2 oxygens, 2 hydrogens. Oxygen has a mole mass of 16, so 16 times 2 is 32. Then 2 hydrogens, so plus 2. Then we have these 8 hydrogens, so I'll just add those 2 to the 8, we get 10. And we get, no, there's 2 there. 2 times 8 is 16, plus 2 is 18. Then 8 times the mole mass of oxygen is 16. And that will be the grams, moles. So the grams and grams will cancel out. And if we add these up, 137 plus 32 plus 18 plus 8 times 16, we get 298. It's 298 grams. Then we take 50 and divide by that. And we get 0.16, or we'll round that to 1.17 moles. Now notice there's 3 here, 1 here, which means that this has to be twice as much, so you can have twice as much there as there. That's clearly not the case. There's much more than that. So this will be our limiting reaction. So we can erase this. Then it says grams of water, so we just have to do a stoichiometry point, and I'll use more. Yeah, 0.17 moles of the barium hydroxide hydrate. And we want to convert these moles to those moles. So for every 3 moles of the barium hydroxide hydrate, we have 30 moles of water. So 3 moles and 30 moles of the water and the barium hydroxide hydrate. These cancel out, and we'll be left with moles of water. Then it says grams, so we have to convert grams to moles. We can look at our periodic table again. For every 1 mole of H2O, I'm just continuing this off over here, we'll have water times and 16. So that's the hydrogen, that's the oxygen, and then we just have to do that calculation. So that should be 30. Oh, it is 30. Okay. 0.17 times 30 times 2 plus 16. 2 plus 16 is 18. So times 18. Then we need to divide by 3. And we get 30.6 grams of H2O. And that's our answer.
Okay, in this problem we are asked to find the moles of iron oxide and aluminum that are used to produce 15 moles of iron, and as well as the mass of aluminum oxide. These are, for the first 2 to find the moles of iron oxide and aluminum, a pretty simple one-step stoichiometry. So we have 15 moles of iron, since there are 2 moles of that in the equation and 1 mole of iron oxide. You do that stoichiometry, you get 7.5 moles of U2. same thing with the other one. Since there are 2 moles in the equation of iron and 2 moles in aluminum, it stays the same. 15. Now to find the aluminum oxide is the same thing, but with one more step, since we want to go to grams here. So we go straight across with this train tracks here, 15 moles of iron, since there are 2 moles of that in the equation, and there's 1 mole of aluminum oxide. And for every 1 mole of aluminum oxide, there is 101.96 grams. So you multiply by the top, divide by the bottom, you get there are 764.7 grams of aluminum oxide.
Just so you know, I'm recording, so you can just start there.
Okay, you recording? Okay, in this problem it tells us if 4 moles of Fe2O3 and 3 moles of aluminum are used, what is the limiting reactant and how many grams of iron can form? To find the reactant, we take 4 moles of Fe2O3, and with that we see that if 4 moles of that were used, since there was 1 mole of that in the equation and 2 moles of aluminum, we would need 8 moles of aluminum. Since we only have 3, we now know that the aluminum is the limiting reactant. Okay. Now using the limiting reactant, we can find how many grams of iron are used. Since there are 2 moles of aluminum and there are 2 moles of aluminum. For every 2 moles in the equation, there are 2 moles of iron. For every 1 mole of iron is 55.85 grams. Right there. 3 moles of aluminum. Okay, put that in a calculator. We get there are equals 167.55 grams of iron.
That makes this a 1.